It's my pleasure to invite Alberto Cavallar. He's talking about surgery links in S3, a short story on Dehn surgery and Kirby calculus. So the floor is all yours.
Thank you for inviting me to give this talk. Okay. This is like the schedule of the talk. First, I will don't be scared about the length of the talk because there's a lot of pictures, and I will try to go as fast as possible. But I wanted to give first like a motivation or introduction about Gene Simons to explain why surgeries are important, and then I'll go in depth in the topic. So let's start with this. I'll try to go fast because I don't want to get stuck in this part. But let me introduce a bit Sharon Simons. We start with a manifold and we give it some structure with a G bundle where we can place a connection and so on. In Sharon Simons, what we want is to obtain a theory where all observables are topological invariants. So as opposed to Young-Mills, for example, where we need a choice of metric, in the Chern-Simons theory, we'll pick a Lagrangian which doesn't depend on metric. And it's there's a choice given by the Chern-Simons theory form, and is given by, and the Lagrangian is given by this integral, where A is a connection on the G bundle. Notice that there's a parameter K. For this parameter, we have a quantization condition, which has to do with the fact that when one computes the, when one applies gauge transformations, the Lagrangian will change a bit. But these changes won't be noticeable in the action if a certain condition for this parameter is satisfied, and the condition is precisely that it must be an integer number. And in quantum field theory, not only do we have to choose a Lagrangian, but we also want to pick some observables which we want them to be gauge invariant. And well, we're going to deal with the so-called Wilson lines, which are familiar in the area of quantum chromodynamics, and these don't depend on the choice of metric neither. So what are Wilson lines? Okay, we consider a loop in a free manifold. We need to pick a representation, an irreducible representation for the gauge, for the group in the G bundle. And then the Wilson line is defined as a certain functional on the connection A. Thanks to having the G bundle and the connection, we can also define a holonomy. So that's precisely the Wilson line. We take the holonomy of A around the loop, and then since we have a representation of the group, we can take the trace of an element of the representation, and this doesn't depend on metric. And this is the definition of Wilson line. And this is a topological invariant, observable, sorry. Just that you bear in mind, this is what we think of when we consider links or loops. This is what we bear in mind. Okay, so having a three manifold, we consider several loops, and we assign a representation for each loop, and then we can propose to calculate a Feynman path integral given by this expression. Yeah, there's DA means integration over all orbits. There is equivalent classes of connections, modulo gauge transformations. And with this, what we get is the so-called partition function, or the expectation value of a given link, which is information is given inside this part of the integral. And that's what we call as Z. Okay, and for the case, the important thing is that in the case of links in S3, what Wheaton saw in his paper in 1989 on the Chern-Simons quantum field theory and the Jones polynomial, he saw that in this case, one recovers the well-known Jones theory of knots. So let me give you a glimpse of what's the connection. We consider a link or a knot in a three manifold, and we apply surgery. So we split this manifold in two, and the knot inside it is composed of a part, which we ignore, and then there's another piece with some intersections. So what we will do is try to replace this piece on the right-hand side by different ones, and then glue it back together. As you may have noticed, we have used for the partition function a letter Z, which is the same we use when we were talking about topological quantum field theories. This is because they're related. Actually, the partition function is the Chern-Simons TQ of T, which will assign. Okay, since we have a closed three manifold here, recall that this will be a cobordism, and the TQFT will assign it a linear map and a homomorphism of the ground field, so it will be an invariant, topological invariant. If we now cut this cobordism into pieces, the elements, the boundary of this cobordism will be assigned to a vector field, vector space, sorry, which will be a Hilbert vector space in this case. And for some point in the boundary, we will assign a vector in this Hilbert space. So that's what the Feynman path integral does. And we have the same for the other boundary over here. Since this boundary is the same with the reversed orientation, the corresponding vector spaces will be dual from one another. So when we glue them back together, what happens to the vectors is just that the partition function sends them to the natural pairing between these two vectors, the one in the vector space and the one in the dual vector space. So the idea is that since these vector spaces, for some reason, the Hilbert vector space is two-dimensional, so any three vectors will be linear dependent. So the point is that since we are going to deal with three of these possible, there are more other possible choices, but we're just going to pick three possible choices for the manifold on the right-hand side, and we will glue it to the other one. And due to this fact that three vectors in a two-dimensional vector space must be linear dependent, we'll get the so-called skein relations appearing in Jones theory. So this is what I was mentioning. We know that we're going to obtain a linear dependence equation. If we apply the pairing, as mentioned before, we will obtain this equation. And finally, when each of these pairing will correspond to the Feynman path integral corresponding to a different link since we are changing the link when attaching, since we are cabling the different parts of this link in a different way, we obtain different links. So we obtain some scaling relation, which are well known in knot theory. They define polynomials for different links. And if we choose a specific group and representations, we obtain the known skin relation, which is, in this case, is a more general one. If we take n equal 2 and do this change variable, then we recover the well-known Jones polynomial given by this skin relation or recurrence, where we need always to pick a normalization, where U here is the R naught. Okay. So why this long introduction? It's been longer than it was meant to. Because we've seen that it's possible to calculate effectively expectation values of an arbitrary link in S3. And one wants to generalize this to any arbitrary three-manifold. And the basic idea is that by surgery on links, as we're going to see, any three-manifold, actually a closed three-manifold, can be reduced to the case S3. So that's why it is important. So it is enough to understand how invariance that we are studying is transforming this surgery. So let's get into the topic. Dehn surgery. I'll start by giving a precise definition about nodes and links, introducing. Then I will talk about what surgery and links in three manifolds is. I will give a short review on the mapping class group of the two torus. Then go back to surgery, but now in S3, which is what interests us, and present the liquidation-Wallace theorem, which is important. And finally, I'll go to a description for length spaces and cipher manifolds. So what is a knot? When we think of a knot, well, the definition is a finite collection of smoothly embedded closed curves in a closed orientable free manifold M. That's a link, and a one component link is called a knot. So let me see. Yeah, I have a picture. What we have in mind is actually we think of a knot as a map sending maybe an interval to and we embed it in a free manifold. But since we want after the whole path to record the same point, we're not going to take an interval but a circle. And since we are going to have several copies, we just use several copies of F1. That's the idea to have bear in mind. We consider a three manifold. We may think of R3, but we will be interested in that the manifold be closed. So actually, R3 won't be R3 manifold. We'll mostly deal with S3, but that's the picture to have in mind. Then we won't distinguish between equivalent knots. The idea is that if you take a knot and you play with it a while without tearing it apart, you have actually the same knot. So we consider equivalence classes of links and knots. Also, it's important the notion of a projection. When we draw a knot, we usually give it by its projection on a plane, where a regular projection is the one where if we take a point in the projection and we look at its pre-image, the condition is that it intersects at most 2 points. So what we'll have in the projection is just that the crossings will be only at most 2 points, and we'll have some number of under and over crossings, like these ones. And also it's important, the notion of a tubular neighborhood. We think of a knot, for example, and the idea is that this knot can be thickened to a whole tube, which is called the tubular neighborhood, and it goes all along the knot, and the core of this tubular neighborhood is actually the knot itself. As said, we're going to consider knot links in S3, which might be thought of as the compactification of R3. So we may think the knots living in R3 for the sake of visualizing them. The point is that S3 is compact, and as mentioned, we want to deal with closed manifolds. Closed manifold is a compact and and I don't remember the other condition. Yeah, it's a compact and some other thing manifold. Okay, let's go now with the surgery. What does surgery mean? Surgery means roughly considering a manifold, cutting the manifold by some curve, and then attaching it again by some other way. This is a precise definition given by you need a map between two topological spaces, and the gluing corresponds to identifying some points in one topological space with the image of those points in the other. The process of cutting has also a precise definition, but yeah, the idea is, as mentioned, to cut the manifold along a curve and then separate the spaces. Okay, now recall what an N-torus is. It's just several copies of S1, the Cartesian product of them. So for n equal 2, we record the 2 torus, which might be thought this donut shape. So the process of gluing and cutting, gluing would be to identify some points in the boundary of the manifold. In this case, we're identifying these opposed edges of this square. So we end up obtaining the 2 torus. Cutting will be the opposite process of, for example, cutting along this line. So we would obtain this manifold. And then we could glue it back together in some other different way. So now, what is Dehn surgery? This is a bit more abstract. Okay, so you consider a knot in a closed orientable free manifold, and its tabular neighborhood, as we saw earlier. And now, by cutting the manifold, the free manifold, you cut it along the 2 torus, which is the boundary of the tubular neighborhood. The tubular neighborhood is actually an embedded 2 torus. So we're going to cut along these 2 torus. Notice it's different from the process we saw here. Here we were cutting along a line. Now we're going to cut, so to speak, along a surface. But the idea is the same. We cut along the surface of the 2 torus. Well, actually, it's the 2 torus. And we obtain 2 parts. The knot interior K, which is the complement of taking the manifold and removing the interior of the tubular neighborhood. This is the knot interior, what we call the knot interior. and then the opaque part we obtain by cutting is the solid torus we're left with, which we identify, as a solid torus. Now the K, notice that K is a manifold whose boundary is a 2 torus, and M is just the disjoint union of these 2 torus and the knot interior. So what one is going to do now is to glue them back together, but with an arbitrary homomorphism, which we call H, between the 2 boundaries. So we're going to glue them back together, but like we are rearranging the points, so to speak. So we obtain a new manifold, which is denoted like this: one manifold glued to the other by the homomorphism H. And what we obtain is again a closed arithmetic manifold, but different from the one we started with, or maybe the same, depending on the homomorphism we're using. And then what one says is that Q, this new manifold, is obtained from M by Dehn surgery along K. This is would be like the definition of what Dehn surgery along knot is. So what one usually does is takes not an arbitrary manifold, closed manifold M, but S3. This is the one with which we are going to work. And then K is not the knot interior, but it's called the knot complement. Okay, observation that the complement of a torus in S3 is actually a 2 torus also. Maybe it's not very easy to visualize, but you may think of a 2 torus and then linking the other one like this, and then blowing this up to all of S3, and so you cover all of S3 since you have the point at infinity. Okay, and observe that the manifold Q does not only depend, depends on which homomorphism we're using, H. Actually, this new manifold is completely determined by the image of the meridian of the 2 torus of the solid torus.
One question, but
yeah.
So the complement so the knot complement in S3 is only a solid torus if the knot is the knot, right? Or maybe I'm mistaken. I mean, for any given knot, is this true?
Not the embedding, but how do you say this?
Well, maybe maybe
I think the idea is that you identify them. It's like a knot is not a circle. It's rather something rather complicated, but intrinsically it is a circle. It is embedding that it's different, but actually like intrinsically it's a circle. So I think the idea is that you have the same. You have a 2 torus intrinsically, but then you embed it in some way in the free manifold.
Yes. What I mean is that given any embedding of your circle in S3, the complement, so the knot complement is always a solid torus. That's no? I mean, point 2. I'm asking about point 2. Just that a knot complement is also a torus in S3.
As a now my camera doesn't.
I think this is not true, no?
No, I think that I think that the whole point is that you think of this as knots inside a T2, and then you take out this T2. O sea, estos nudos los puedes imaginar en un T2. Ahí no sé, no me funciona la cámara ahora.
¿Ah, sí? No.
Sí, estos nudos son una lista de nudos que los imaginas.
Sí, pero Pero estos son los torus knots, pero no está hablando de torus knots, ¿o sí?
Yo creo que para la clasificación de licorice, que es la que va a explicar ahora, es suficiente con usar esa lista. But de todas formas, what Alberto is saying is also true, that you are not thinking of an embedding. You are thinking that this is homeomorphic to S1, but not embedded.
Robert,
yeah. Maybe Robert, you're right, and it's not very well written.
Well, let me check this. I'm just curious.
On the other hand, I think that you are going to be working with not that this. Let's see, these torus, you can think of them on a T as knots on a T2, and then it's even true. That's what I think. That's what I think licorice has, right?
Yes. But I mean, what's written here, it's so if you take a knot and you take a neighborhood, which is a solid torus, and you take out the solid torus, you get a manifold with boundary, which is not going to be a solid torus in general. Only if the knot is the unknot.
Yeah, probably it's. I haven't written it.
Yeah, sorry, I have missed you because there was no way to fix my. I mean, okay. But it's too general. So what I think, Robert, that you're asking the general question, but here we are considering specific type of knots because what Alberto
But I mean, the statement like this, I think it's not true. Well, I don't know. I mean, if you pick one knot and you take the knot complement in S3, that's not going to be a solid torus always. Only if the knot is trivial, so to say.
Exactly. But you have that these knots are lying on a T2. They are torus knots. Right, Alberto? Am I right or not? Correct me.
I don't know. I'm confusing myself now.
So only know what
you
need to do.
I mean, yes. Okay, if knots are torus knots, then it's my.
Okay, yeah. Yes. Then just forget the statement. I think I haven't.
Well, maybe go. Do you have the slide of the theorem of licorice and Wallace?
Yeah, it's coming, I think.
Yeah, don't worry. I mean, it's just to...
Okay, we'll see. I don't know what's going on with my camera.
So the idea is that the manifold will be determined completely by the meridian of the torus. By this curve. So actually, the image of the meridian of the torus by the homomorphism. Okay, so before explaining this, I'm going to review what the mapping class group of the torus is. I start with recalling what it means. The two homomorphisms are isotopic. This is the precise definition. So what the mapping class group is this quotient where homeo F is a surface, and this is a group of all orientation-preserving homomorphisms of a close-oriented surface, and homeo sub-zero is the normal subgroup with those which are isotopic to the identity. So we can consider a quotient, and we have this. I think, I'm not sure, but I think we can imagine this as like kind of a fundamental group, but considering isotopy classes instead of only homotopy classes. And this is what the mapping class group is. Also recall the.
You have example of this mapping class group that you have.
Yeah, I'm just going to give the mapping class group of the two torus. That's the example I'm going to give.
Great.
But first, I want to speak a bit about the Dehn twists. This is formally how you can define them, but the idea is that you can take a piece of your manifold and kind of twist it, and by this map, and a Dehn twist would correspond to twisting it like one whole turn. Okay, so there's a theorem that tells us that for a close orientable surface of genus G, the mapping class group is generated by these Dehn twists along these curves. Now we we will deal with some with only the two torus. So we will have that the mapping class group will be generated by just two curves, which will be a meridian and a longitude by 10 tweets along these curves. So yes, now the example. If we consider the two torus, we can and choose generators of its fundamental group. So a pair of integers. You may think of the two torus as the boundary of the solid torus embedded in R3. Then you choose the standard coordinates, angle coordinates for each copy of S1. And so the curves corresponding to theta equals 0, psi equals 0 are called the meridian and longitude. These curves are different, like play different roles because the meridian is this one. It bounds a two-disk in the torus, while the longitude does not. Actually, the longitude can be, I'm not sure about this now. Yeah.
What is not?
Yeah, I think it can be contracted to a trivial curve, but if you consider the complement of the torus, then the longitude can be contracted, whereas the meridian cannot. That was what I was thinking. So these curves give generators for the fundamental group of the torus. We can pick an orientation, like choosing a basis of the Dehn space, and that's what we're thinking of. You can take combinations of meridians and longitudes, and then you get different curves turning around the surface of the torus. So now this functor pi1, which sends a topological space with a fixed point to its fundamental group, and also it sends a map between two fundamental groups. You can, I mean, if you have a map between two topological spaces with a fixed point, then you can define a map between the corresponding fundamental groups, because for a given loop in X, you can define a loop in Y by taking the image of the loop. So this functor converts a homomorphism F of C2 into group of automorphism of its fundamental group. Now, automorphisms of this fundamental group, I think of it, will be given by 2x2 matrices, and since it's an automorphism, we need that they be invertible, and they must be defined over the integers. So a matrix is invertible over the integers if and only if its determinant is plus or minus 1, as can be seen here, where the denominator is plus minus the determinant. Actually, it's minus the determinant in this case. Okay, now the matrix of this automorphism corresponds to an orientation-preserving homomorphism, or F, if and only if the determinant is equal to 1. If it's minus 1, it would be an orientation-reversing homomorphism. So we have a well-defined homomorphism between the mapping class group of C2 and SL2Z, which is the group of integral 2x2 matrices with unit determinant. Just as we've explained here, we send the generators of the mapping class group. Sorry, in this way. Each matrix in a Z2 set can be reduced to identity by elementary transformations, rows and columns. And so each element in this group is a product of matrices of these forms, where these matrices are realized by Dehn twists along the meridian or the longitude, respectively. So we have a theorem which guarantees us that this map defined here above will be an isomorphism. So we have corresponding between the elements of the mapping class group and 2x2 matrices of the integers with unit determinant. So we may think instead of talking about the mapping class group, we can talk just about these matrices. Now the isotopy classes of orientation reversing homomorphisms. Yeah. Now, since we're dealing with orientation reversing homomorphisms, this will be in one-to-one correspondence with these determinants, but with these matrices, but with a -1 determinant. Such matrices are of this form: TA, where A is as above, and T is just this matrix, and is realized by the torus homomorphism given by this mapping. Okay, so now the manifold, consider a manifold M obtained by gluing two solid tori by an orientation reversing homomorphism between the two tori between the boundaries. So the meridian, we're going to look at where the meridian and the longitude, which are bases of each tori. We have two bases. We want to look where this meridian longitude are sent to by the homomorphism F corresponding, which will, instead of considering the homomorphism, we will look at the corresponding matrix. So we have one such given matrix, an arbitrary matrix like this, where we require the determinant to be 1. And yeah, in particular, the image of the meridian is given by this expression. It's isotopic to this curve, which is winding minus q times in the Z2 direction and p times in upside 2 direction on the second torus. So there's a lemma that guarantees us that we just need to look at the image of the meridian to completely determine the manifold. Intuitively, this is given by this first. The meridian corresponds to this first column, and we really don't care about the second column, so to speak, because we have the condition, this condition, and the fact that all entries must be integer. So in the end, what we've seen is that the manifold M can be completely determined by two integer numbers, P and Q, and which are co-prime to one another due to this condition. This is what we call a length space, and we denoted LPQ. Okay, yes, mentioned PQ will be relatively prime. So there's a theorem that tells us that any 3 manifold of genus 1 is either this manifold or a length space. That's why length spaces are important to us.
What is genus in dimension 3?
I think it's Hegel genus. I don't remember precisely the definition.
Yes,
but it's Hegel genus. Okay, so let's come back to surgery in M, but we are now going to consider the specific closed 3 manifold S3. Okay. Well, okay. Now one can see that a curve on the boundary of the not complement.
Alberto, can you go to slides? Can you show me 2 previous slides? The previous slide or the other one? Yeah.
This one?
So yeah, exactly. So the G-guard, coming back to the question of Robert, did you define what is the role of H-guard in this business?
No, I think I didn't define it.
It has to do
So
with
probably it's a
handles,
dimension of
no?
this H-guard group or the here flower group probably has some generators, and then we copy the word genus because there are generators for some H1, right? That's what you said or not? I missed that.
No. I asked
Things
for what
related
it means.
to-
No. I asked
What
what
is
it
the
meant
meaning of
genus, and he
genus?
said it's Hegar.
Yeah, exactly. But so what I'm asking here is exactly where these genus, how the genus are defined. So probably some Hegar homology group, and then the Hegar homology group probably has some generators in H1, and then you copy from the 2-dimensional case in which you call genus the genus, right? The genus, which is given by the H1 in the standard homology. So what I think is that this Hegar genus corresponds to looking at the first Hegar homology group. That's what we should check.
I thought you could define this using a handle decomposition or something.
Probably you can define this, but I mean, okay, let me transform this as
related to handle decompositions.
What?
Yeah, but can you fish it? Can you fish it through the Hegar homology or not?
I don't know.
Have a way to abstractly. So this is for Pablo. Do you have a cohomology to capture this genus? That's the question. Probably, like I mean, maybe the Hegar homology is going to give you that. Have the same name, and it's an homology. So maybe the genus.
But what is Hegar homology?
The Hegar homology, Hegar Floer homology. You don't know this?
No, Hegar Floer, yes. Okay.
This is in the paper of Kukov-Manulescu too, right? So essentially, they are using it to produce some computation. So it's essentially they don't care about the definition, but let's say it's an homology, right? So it measures some invariance, and what I'm suggesting is to check. I don't know, but my guess is that the Hegar genus can be read from these homology groups.
I guess
that's what I suspect, right? And I think that they use somehow this homology in the paper of Kukov-Manulescu. I didn't have time to check, but Alberto, this is one of the things that you were reading, right?
Yeah, but I can't remember the precise definition.
But the problem when you are in Caltech is that everybody says, "Oh yeah, Hegar Floer homology, cool," but or Hegar homology or whatever. But then, who can compute this, right? So maybe, I don't know. So my guess is that these moves, you can read them in some homology, and probably it's this Hegar homology. I don't know. We should check. I don't know how to pronounce this because Hegar is a Nordic. Hegar. Strong voice. I don't know, because probably from some northern country without sun, ¿no?
Yeah.
¿Quién es Hegar? No sé.
Hegar, sí.
Pero seguramente hay una homología que captura estos movimientos. Y debe venir de ahí, yo creo, ¿eh? No lo sé. Deberíamos comprobarlo.
Sí. Pero, porque, o sea, a mí me suena que, en plan...
Porque se puede calcular. Se puede calcular, vamos. Hay una forma de calcularlo. Luego vete y calcúlalo, ¿vale?
Entonces, jo crec que, o sea, vale. Però el genus no sé si està definit per tota varietat. O sea, el genus 1 debe ser que las handles son como de dimensión 1 o de codimensión 1, que entonces son solitorios. Pero...
Vamos a ver, Hegar genus. Vamos a decir qué dice Google. Google dice, pues en el Hegar splitting, Wikipedia. Está en Wikipedia, vamos, que lo deberíamos saber. Danish. Y además lo pronuncia.
Hegar splitting sí que va en slide.
Hegar.
Handles.
Google dice. Entonces, a ver, es que claro, no necesitamos saber nada. Todo está en Wikipedia, pero la tenemos que leer. Entonces, aquí hablan del splitting de Hegardt en esto de handle bodies y eso te da un tree manifolds. Vale, aquí te lo explica todo. Wikipedia está todo. Pero no habla de una homología. Yo sospecho que que la homología de Hegardt lee este género. Classification, bla, 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 bla. Sí, mira. Applications and connections, Hegardt Floer homology. Hegardt diagrams, which are simple combinatorial descriptions of Hegardt splittings, have been used explicitly to construct invariants of tree manifolds. The most recent example is Hegardt Floer homology. The theory uses the gist product. Vale, no te dice si el genus tal, pero vamos.
Ah, sí, pero es esto, ¿eh? O sea, BW handle bodies of genus G. O sea, si la variedad se puede construir con dos handle bodies de genus 1, entonces tienes
vale, ya lo tienes escrito en la tesis. Qué bien.
Sí, solo que no me acordaba de la definición.
Vale.
Pero sí, es esto de los handle bodies.
Guay.
Vale.
Bueno.
Muy bien. Jolín, Alberto, estás estudiando un montón de cosas, ¿no? Estás a tope.
Sí,
no tienes tiempo de ir a comprar, eso está claro. Espero que te den la comida preparada, porque si no... Vale. Interesante, perdona.
Vale, voy a intentar darme prisa, que se me va el tiempo. Okay, so we consider now surgeries, but in S3. As said, one can see now a similar a curve on the boundary of the knot complement, which is homomorphic to the two torus, will be given up to isotropy, but by a pair of relatively prime integers P and Q. So by one considers the homology groups of the knot complement. So any meridian of the tubular neighborhood represents a generator of the first homology class, and this curve on the boundary is what we call M, thinking of the meridian. And up to isotropy, there is a unique longitude. Unique if it's the one which is homologically trivial in the knot complement. So in the complement, you can contract it to a point. This gives the other curve on the boundary, which we think of as the longitude. And these two form a basis of the homology class of the boundary of the knot complement. Okay. So yeah, we won't care about reversing orientations of meridian longitude. And we give an orientation as shown in this picture with a normal vector to the torus. This gives an orientation to the boundary of the knot complement. Okay, so now a simple curve on this boundary is now isotropic to a curve of the form of this form, like winding P times the meridian direction and Q times longitude. So one can conveniently think of a pair PQ.
The boundary of K is at T2 or not here? Sorry, I missed this from the previous. It's a no or not?
I'm confusing with the
T2. Yeah. So it's a torus knot finally. Okay, perfect. Good. That's important.
This is homeomorphic. I don't know. I'm confusing myself now.
It's homeomorphic. Well, it's diffeomorphic probably. Otherwise, you wouldn't be able to put this expression here, which is the decomposition of a torus knot. You can think of these the generators of the two torus, M and L, and then the P and Q are these coefficients, and this is a rational knot. Okay. So lo puedes ver como una curva dependiente PQ, P sobre Q sobre un toro, que es una forma de sobre el toro plano, y entonces esto es como está anudado en un T2. Y ahora volvemos a la imagen esta de que efectivamente podemos pensar que esté en un T2 en la teoría esta. Perfecto.
Sí, creo que esa es la imagen. Sí.
Que además el dibujito aquí está bien ponerlo. Pero bueno, yo ya lo tengo en la cabeza, pero realmente está en un T2 todo esto. Perfecto.
Okay.
Me alegro.
And this reduced fraction PQ is what we call the surgery coefficient of the knot complement. So we have a one-to-one correspondence between isotopic classes of non-trivial simple closed curves on the boundary and a set of reduced fractions PQ, which is completed with the fraction corresponding to the infinity, which corresponds to winning only around the meridian. Yes.
By the way, given a torus, I know that you want to reach the end of your slides, but just for general culture, I want to explain that given one of these torus knots, you can always associate a singular curve with some Bezier coefficients. The people who studied algebraic geometry I don't know, is there anyone here who did algebraic geometry? Marc and Lara? No?
Sí, jo estic fent. Encara no m'ha arribat, però...
Llavors esteu fent aquells invariants de les corbes planes on teniu aquella descomposició de Bessut, no?
Sí.
Pues
ara...
Sí.
Al següent tema volem fer això, crec.
Vale, doncs hi haurà un moment que hi ha una connexió amb torus knots. Si teniu que fer un treball, demaneu fer un treball de torus knots.
Vale, li diré a Pere Pasco.
Ja us passaré un article. Bueno, jo quan estudiava ho vaig veure molt xulo.
Vale,
perdona, Albert.
Perfecte.
No, pero sale geometría algebraica aquí. Sale un poco de todo. Me callo.
Okay, and then with surgery along this type of curves is what we call PQ surgery. So this we call this rational surgery if, since we're dealing with rational numbers, and we will call it integral if this will be an integral number, that is if q is plus minus 1. Similarly, one defines rational and integral surgeries along a link, so several knotted knots. And this is an observation. We do 1/0 surgery, one on any knot, then you record again S3. In the case of links in the 3 sphere, there is a canonical choice of the longitude, which is that every you take at each component of the link, every longitude is chosen so that it is null homologous to the knot complement, in the knot complement.
Do you have an example where you can recover from the with one of these from the S3? Do you have a visualization of these surgeries with a particular knot, like I don't know, the 3-foil knot, el típico nudo, the 3-foil, the 3-foil.
Yeah, I really don't have an example.
That would be cool if you can do this. If you can do a film of how to do this, this would be really cool for the presentation. Maybe this film exists because there are many people working on the field of, you know, 3-dimensional topology, and probably somebody has done, should look at it, some nice visualization of how you do these surgeries. So essentially you have S3 and you do a surgery and recover some other 3 manifold. Of course, you need to do some kind of projections to visualize this, but it would be cool to see some of this.
Can you go back to the definition of integral surgery? I don't remember.
Well, yeah, it's
yeah, integral is that the p's and the q's that you don't have a denominator. So because you do p over q, the slope is integral.
Però la surgery què és? Enviar la meridian a PQ.
Treus l'entorn del nus i li pegues una altra cosa. És el que ha explicat.
Vale.
És el que explicava al principi.
Sí, però sí, el que no entenia és el de... Però que he deixat d'escoltar un moment, per això no...
Sí, al principi, exacte. Quan tu no tenies bona connexió, doncs ha explicat com es feia la cercle.
Sí, agafes el cercle que està en el core i l'enganxes en el PQ girat, no?
Sí, bueno, entonces, ¿cómo interviene en esta surgery? Por cierto.
Creo que no es la curva del core, sino creo que envías es la imagen del meridian.
Ah, vale, bueno, vale.
Porque ves que solo te basta con definir a dónde envías el meridian, o sea, por dónde te vas.
Sí. O sea, vale.
¿Y el Dehn twist aquí cómo aparece con el surgery? ¿En el otro haces un Dehn twist de Q o cómo?
Es que es lo mateix, ¿no? O sea, enviar la curva del meridiano a PQ es como hacer un PQ Dehn twist, me parece.
Sí, exacto.
Por eso, pero es que claro, esto es más visual, por eso digo, ya que lo ha explicado, que lo ponga todo junto. O sea, la gracia es que lo del Dehn twist aparece aquí. Puedes explicar,
o sea, pegas la boundary del solid torus con un Dehn twist.
El Dehn twist es una anotación muy guay para decir que estás cogiendo, pegas y giras y vuelves a pegar. Vamos, dices, ostras, me cargaría esta persona, voy a hacerle un Dehn twist. Pues te coges del nudo y le giras la cabeza y lo vuelves a pegar. Madre mía, violencia, esto queda grabado, qué horror.
Sí, todo esto está grabado.
Que en Estados Unidos, si no me echarían de la universidad. Bueno, o sea, un Dehn twist sencillamente es hacer este gesto y volverlo a pegar. ¡Pam! Lo que pasa que es que nadie se atreve a explicarlo así, pero es eso. Y va bien para hacer las surgeries. Bueno, te estamos cortando a tope, pero bueno, es que es para que todo el mundo lo entienda, ¿eh? Yo incluida.
Sí, no, perdón.
Es brutal, ¿no? Esto es como súper brutal. La pregunta es, ¿el teorema de Licorice y Wallace? El toro entendemos que es T2 todo el rato, ¿eh? Dentro de ese 3.
Yo creo que sí. No sé, es que hay que revisar.
A ver, la definición que estás dando de nodo es que está en T2.
Sí. O sea, el teorema es ese. O sea, coges un link, coges los toros alrededor, haces Dehn twist en los toros y ya estás. Y eso te da cualquier variedad. Seguro.
Es como muy brutal.
Sí, es muy fuerte. Entonces,
lo que pasa es que el link depende de la 3 variedad que quieres obtener, claro.
Esto es la letra pequeña que nos explica Gukov, porque Gukov dice, tengo mi varita mágica, hago mis integrales, fijaros, no sabéis que estoy integrando, jaja, tengo mi programa de ordenador. Es como dio la charla.
La gracia,
muy clara. Di, Alberto.
Sí, no, justo al final de la charla lo quiero juntar con esto de Gukov, porque la gracia está en que, o sea, con diferentes links tú vas a tener diferentes tree manifolds y entonces, bueno, es que lo voy a explicar ahora. No sé si pasa directamente.
Vale, adelante, aunque te tengas que estar más rato, no pasa nada. Que te hemos estado, Roberto y yo, te hemos estado en sentido positivo, para que se entendiera.
Vale, entonces, the point is that not only it's important the link along which you do the surgery, but the choice of these curves we're talking about. That is, we need to assign a reduced fraction to each component of the link. So such a choice is what we call a framing. And a link with such reduced fractions attached to each component will be called a framed link. And this information can be, we can draw it like this. And with this information, we can define what a closed tree manifold will be by thinking of this tree manifold as the surgery on this link in S3. With these surgery coefficients. An important thing, then remember we talked about length spaces because there was a theorem that told you that almost all of these manifolds were going to be length spaces. So you can construct more or less explicitly how this construction goes, and I will skip this a bit fast, I think, but you can think of, you start by considering LP1, and you can see that it is given by certain homomorphisms. And in the end, the picture to be in mind is that you're gluing by doing p turns or minus p turns, meridian turns for each longitude. So what you describe it by drawing a circle and a surgery coefficient along the circle, and you can do the same for to obtain LP PQ in general. There is a whole construction which I think is standing off for now, but you can do some gluings, and finally you end up with this surgery of 2 knots, with each of them with a surgery coefficient. And if you compute the corresponding homomorphism, which is the composition of these maps, the idea is that you do the construction for LP1 and for LQ1, and then you glue these two constructions, and you get this gluing map. If you look at the first column, which determines the meridian, you see that this surgery corresponds to these lens spaces. So we know how to construct lens spaces by surgery, which we can describe with diagrams like this. So there is a theorem that tells you that that any lens space has a surgery description, like in this figure, where you have a chain of knots but knotted with one another, and the framing of each circle corresponds to the numbers appearing in a continued fraction decomposition of the reduced fraction at PQ, where the continued fraction decomposition is given by this expression over here.
One question.
And why this expression appears can be understood when looking at the proof. Was someone trying to ask something?
Yes. One question. So, like this, you do it to have integer, no? Coefficient, or what? Okay.
Yeah. We want to have only the thing is that we can see that we can deal only we don't have to deal with rational surgeries, but we can just do integral surgeries.
Okay.
And this is done by computing the continued fraction decomposition. Also, you might have seen these diagrams, which represent the same. Each circle is going to be a node. So each circle is going to be a vertex, and each link is like two vertices linked together. Will be joined by an edge. And
so this is the same picture of the talk of Sergey at the beginning.
Yeah.
And then when you have, because I imagine that you have this kind of graph, like, I don't know, only in one line when you have a lens space. But when you have the graph that he was showing, where you have two spikes,
then I'm going to show it now.
Is that?
I'm going to show it now. It's called a ciphered manifold. It's kind of a generalization of lens spaces, although I'm not going to describe them very well. But yeah, why this continued fraction decomposition appear can be seen in the proof. It's just by doing induction. You consider the previous one is given by a continued fraction decomposition. Then you compute the corresponding matrix. How would it be? You look at the first column and you just compute what the fraction would be, and you notice that is exactly the definition of continued fraction. So you end up having the continued fraction. And every rational number has a finite continued fraction of this form, so the proof ends. And that's why the continued fractions appear. And as said, if we consider general ciphered manifolds, which I'm not going to describe now, but they have a precise description. These cipher manifolds are kind of a generalization, and they're given, the surgery is given by this picture over here on the left-hand side, where we have a non-knot with a 0 surgery coefficient, and then several circles, each with a reduced fraction framing. And if you apply the same reasoning as for each of these ones, you take the continued fraction, the composition of each of one, you obtain, and you, instead of thinking of links, you consider the graph. You obtain this graph decorated only with integer numbers.
And does it work for graph manifolds?
Sorry, Robert, you're asking the same. Go.
What's the question?
I was asking if it works for graph manifolds, which is a little bit more general than Cipher.
What?
You know this. If it works for graph manifolds. Because graph manifolds are just Cipher manifolds with boundary glued along their boundary. So it's almost a Cipher manifold.
But maybe you don't need, from the description of licorice, maybe you don't need to deal with them. No, with the graph manifold situation.
Maybe not. Yeah, no, but I was just wondering.
Like, it's enough to have this Cipher description, no? Because it's a kind of...
I think you consider just like trees, tree graphs.
But I mean, like, can you get any 3 manifold with integer surgeries on a good link? Or is this true? Or?
I think it is, but I'm not sure now.
Okay.
Because the knots are rational, and then you make this kind of the composition.
Yes, but I mean, like, what he has proved now is that for Cipher manifolds, you can find a suitable link in which an integer surgery works. But my question is, does it work for any manifold? Maybe it's more complicated.
You jump from the rational to the integer with this decomposition, right? So for the rational case,
no, but this only works for a Cipher manifold. If it's not Cipher, I don't know if it works. No?
The previous one, the easier one, the length space before Cipher. Yeah, what I think is that probably this is enough for what he needs to do for the licorice theorem.
Yeah, I think it's enough because I don't know if I'm confusing, but I think I showed a theorem where it said that all of the 3 manifolds we were considering would be or S2 times S1 or a length space. But I don't know if that applies now, because I don't know why then we are dealing with Cipher manifolds and not just length spaces.
Because you may have a situation like this picture is showing you. You might consider this kind of this picture. What is the difference between this picture and the former one? Is that you are gluing this other situation, and that's when you get this cipher. Indeed, the description of how you go from A1, B1, AN, BN to the manifold can be done topological, right? It's a kind of mapping situation, at least the one that you have here in this picture. So let's say topologically, it's not enough, the length space. You may have generate.
The kind of links are very simple. Like for the length space, you're just taking links that are pairwise linked, and this also is very easy. It's like one link, one knot, and all the others linked with it. So if you take more complicated links, maybe you can get other manifolds.
Yeah, exactly. And then you're adding like other. What are you following for understanding these 3 manifolds, this licorice Wallace reference, Alberto? What is the reference?
From Nikolai Saveliev. I'm going to share it at the end, and the references. There's a book from Nikolai Saveliev on topology of 3 manifolds or something like this.
Okay.
Well,
maybe we can
solve this. Yeah, let's go on, because I was just curious.
Well, this is very cool. I like it.
So now the last thing to consider is that with these graphs or with these diagrams, you can obtain any close oriented C manifold, but what we may wonder if different graphs may give rise to the same three manifold, and this is indeed true. And so we can consider how to see the equivalence classes of such diagrams which give rise to the same free manifold. And these equivalence classes are given by the Kirby calculus, which I'm going to explain fast. First, you need to define the linking number. There are different definitions, but the most simple one is to consider just consider two links, and their linking number can be computed in terms of counting the number of such undercrossings and computing +1 if it's of this kind, or -1 if this kind, and summing all together, and that gives you the linking number. So also the linking number has several properties. It's symmetric and so on. And with the linking number, we can define properly the longitude. Longitude will be such one that the linking number of the longitude and the knot will be 0. And also, with the orientations chosen, we see that the linking number of the knot and the meridian is going to be +1. So these are like equivalent forms, views. Yeah, to view what we're talking about. We can think of a link with a framing, or just a band which is winding around, and this is the definition. We have the knot, and we consider a longitude going next to it, and by computing the number of undercrossings with the specific orientations, as shown before, the plus and minus signs, you can compute what's the linking number by looking at the different contributions all along the diagram and stringing them together. And the longitude, as said, is defined so that this linking number, has to be 0. So it is well defined. So now, which are the Kirby moves? There are 2 moves which have a precise definition. I'm going to show you the diagrams. The first move tells you that you can get, actually, these are reversible moves. You can go in either direction. The first move tells you that you can get rid of any unknotted ±1 framed circle, and the other one tells you how you can. This is called sliding. The second move is called sliding a link over another. So, for instance, L1 sliding over L2 means considering a framing of L2, like that is a longitude, and then taking a band and connecting this longitude to the link we had before. So L2 remains the same, but now we replace L1 we had with this new link, and this is the second move. The framings of all components remain the same, but the one for L1, which now will be L hashtag, and its framing will change by this number. So we know how framings change. We need to fix an orientation, and this orientation for the new link, and this orientation will depend on how this band is glued. If it's twisted, you have a different orientation. You just orient each part of the link so that it is compatible, so you don't get reach points with different orientations, so to speak. So the theorem of Kirby tells us that it's sufficient to consider Kirby moves No, it tells us that Kirby moves, if two surgery descriptions are equivalent in terms of Kirby moves, so you can move from one picture to another by Kirby moves, then the close-oriented three manifolds we will obtain by integral surgery will be the same, or homomorphic. And then there are several rules which can be computed. This proposition tells us how we should work out these rules. If we have a circle with ±1 framing and several arcs going around them, tells us that we can replace them. We can remove this circle with ±1 framing, which we can then remove according to the first Kirby move. And these arcs will be, assuming they represent different components of the link, what you have to do to them is apply a full twist and change the framing by -+1. So like in opposite to the framing we had here. Recall what a full right twist is do something like this. For the n=1 case, we have these rules. So the translation is these rules. For the case of two strands, we can see how the twist goes. So this gives us how we should compute. Now I'm going to give an example. Notice that these links are precisely the twist we have here. So if we have two circles and noted with a -1 framed circle, it tells us that we can remove this circle in the middle, and these two link them together. And this link is given by the twist given over here. And it tells us how the framing should change. So that's example. We can see how we can work. If we have this diagram, we can, for example, add, I'm mainly going to use this movement, which can go in either direction. So you can also add a new link, and the framings will change. And once you've added, you can do this in several parts of your diagram. And once you've added, you get here, you have to play with the plus and minus ones. You have added a +1 here, but now you can use the -1 here to contract this link together. And you can do this in an iterative process. So shrinking the diagram to a simple one, and this can further be, with the same rules, can be simplified to this one. So we can see, this is an example of two different diagrams with which will give rise to the same three manifold. So now linking with the talk from last Thursday, now you may understand a bit more what was meant when we considered, when Sergey was considering graphs framed by integers, because they correspond to these surgeries with integral coefficients, and the integrals applied were actually the surgery formula defining an invariant, a topological invariant, which is actually a Q-series invariant of three manifold.
Can I ask a question, Alberto, that I didn't ask to Sergey? Like the integrals that you put here, these mysterious integrals that, of course, are associated to the Q. So there is a Q in this formula that is associated also to these A's. This is something that was. How do you describe these terms that you are integrating? I mean, the formulas that he was giving some formulas for what you integrate, but what was the relation to the? Can you explain?
I haven't really seen that part, so I really don't know. I understand that you there's another theory or something that tells you which coefficients you should assign to each edge and to each vertex, so as to define the integral. But I don't know where this integral comes from.
The coefficients he was associating to the graph, the matrix of relations of the graph. I don't know what's the name. This is a matrix, and then this with this Qij, he was associated when you integrate, and then these Xj are related to the AIs in the formula, right? But what you integrate, well, if in his talk he was saying that this is in his paper, in one of his old papers with Barma and so on, that you have to integrate that specific expressions. But I don't know. I wonder if you had time to look at that.
No, not yet.
This would be cool. Be cool. So essentially, but you are going to have to do that, right? Because for the case of you have to do the program in Python and to do that or in Mathematica. But to do this, you need to know what you have to integrate, right? The formulas.
Yes. This is work yet to be done.
This is not an abstract thing like Pablo likes, like a diagram that commutes. No, this is a formula with an integral and some coefficients, and this is Mathematica programming and so on. Yeah. But
I think the point is in the program, you won't do this integral. I think you translate it to what Seung-Yuk did in his last paper. He translated to the realm of quantum groups and so on. So in the end, you don't have to deal with these integrals, and you can work with R matrices and so on. But this is what I will learn this coming weeks.
Right. This is what Seung-Yuk did, essentially to play with the R matrices. R matrices is another fancy word for a sophisticated mathematical object. Warning. So if you like, it has, it has the word matrices, so you think this is going to be very easy. Go to the R matrices door. It's no, I mean it's not difficult, but I mean it's another concept. Like this is what Kolya Resetikin is working on. So maybe Pablo, in your next life, in your next reincarnation, when you go to China for an undergraduate thesis, then you could do this. Maybe. Okay, thank you.
Okay, so these are the references.
And these are the lectures that you were referring to in what you sent me.
Yeah, mainly the second one.
You have this? Do you have this?
Yes.
Can you share with us in some kind of Dropbox or something? Or it's available online? Yes. The lectures are
yes, I can send it, I think. Yeah.
This is very important also so to Lara and to...
Well, are there more questions about the talk? I mean, there has already been quite a conversation.
Do you want more questions?
Okay. I'll stop. I'll stop the recording here.
Stop recording because we had too many secrets.